play a big role.
And then it's gone, the meltwater is gone unless there's a lot of snow or something later on.
Yeah, that's right.
So let's just kind of backtrack, because you're kind of going way above my understanding. How does this weather, how does this meteorological phenomenon and processes play into an ecosystem? I wonder if you could kind of just break down for us this energy balance.
Sure. So it would seem like a no-brainer, right? You have this ice. If you increase the temperature, you get water when it's above freezing, right? And the higher or the warmer the temperature is above freezing, the more melting you get. I mean, we kind of know that from snow on our sidewalks. How fast it melts away is based partly on, you know, how warm the air is. Well, down here, this is true everywhere, but it's kind of better highlighted down here, and that is the warmer the temperature maybe melts the ice more, but then the dry winds come through and it evaporates the water. So for us, really, then, it's a competition between how much water is produced and how much is evaporated. And you can actually, you can see this kind of demonstrated by analogy back home when you see the rain coming from the clouds and it never reaches the surface. That's because there's rain coming out of the cloud, but it's evaporating so fast it never gets to the floor of the valley. We're, in the same sense, these glaciers are melting water, but they're also evaporating at the same time. A more subtle aspect to this is when the temperature is actually below freezing a little bit. The sunlight can warm up the ice to cause it to melt. The air temperature can be below freezing a few degrees, but the ice surface can be above freezing due to the warmth of the sunlight. If the wind is fairly calm. As soon as you get any amount of wind, that wind removes the heat, keeps the ice surface frozen. So then it becomes a competition between how much sunlight there is, air temperature, and how much wind there is to remove the heat. In a sense, like wind chill, you know.
Right.
And that's kind of that's kind of the basis of the energy balance, is this competition of processes adding heat and subtracting heat. And because our system is fairly close to freezing, we get pretty dramatic responses due to small changes. If we were really cold, like in the wintertime, not much happens despite big changes in the environment. Kind of like what we talked about with katabatic winds. So what if it raised the temperature 10 degrees?
Right.
If it goes from minus 40 to minus 30, nothing happens. Similarly, if it's really warm and it's, say, 10 degrees and goes up to 12 degrees, yeah, you get some more melt, but nothing really changes. It's that threshold between below freezing and just above freezing, no melt and water everywhere. That's kind of where we're at.
Where there's a transformation from the solid state to the liquid state.
Right.
Now, Matt and Hassan were telling me that, or suggesting that the energy balance, that there's this energy balance equation. It's a very simple equation, but then when you kind of put it into practice, it's really complex.
That's right.
Is that right? What is the equation?
Well, the equation simply is the amount of sunlight coming in versus the amount that's reflected. So it's kind of the net amount of sunlight coming in. And then you have the wind, which not only, depending on the difference between the temperature of the air and the ice, either brings heat to the ice or takes heat away. So if the air temperature is warmer than the ice, it'll bring heat to the ice, or vice versa. The wind also has humidity. So if it's really dry, it'll tend to evaporate the ice. Or if there's water present, tend to evaporate the water. So depending on what the humidity of the air is, it can take more or less heat away. And then because our average temperature is like minus 20 C here, there's conduction, ground conduction of heat as the surface of the ice warms up due to either the air temperature or the sunlight. The heat at the surface will begin to become conducted down into the body of the glacier where it's really cold.
Right.
So sunlight warms the ice, wind can either add heat or take away heat. It tends to evaporate the surface, which is a heat loss. And then there's heat conducted from the surface into the body of the ice. And then when you add all these up, you either have energy left over for melt or not.
Oh, okay.
And if you don't, it cools the ice.
So your elements of the equations are wind, sun, and conduction of the ice, basically.
Right, yeah.
And then how do you measure each of those elements? Do you measure the elements separately and then kind of make the equation, or?
Well, pretty much. The weather stations that you saw out there tell us what the wind is doing. It tells us what the humidity of the air is doing. It tells us what the air temperature is doing. Then we have thermometers in the ice that tell us what the ice temperature is. So we know the difference in the ice temperature. So we know something about the heat being conducted in. We know about the wind, so we know about the addition or subtraction of energy through the wind. And then we also have solarimeters that measure the intensity of the sun coming in. And we also have an additional device that measures the reflectance from the ice surface. So we know the net amount of sunlight that gets into the ice. You know, it's the difference between the amount coming in and the amount being reflected.
Right.
But there's subtleties with this that make things difficult, actually.
For example?
There's two things that I think of offhand. One is just the difference in surfaces across the glacier. Just because you're measuring what you are at that one site doesn't mean 10 yards away it's exactly the same.
Right.
And, you know, weather-wise, it's pretty much the same, but the difference might be snow cover on the surface. This might be bare ice, which is less reflective than the snow-covered ice just over there. Big difference, because since that has more reflection, it's getting less solar radiation into the ice, much less heating of the ice, and that's completely different, energy-wise, than this piece of bare ice here.
Right.
That's one thing. The other thing is that because we're right near the melting point, like I said, small differences in the meteorological environment can make a big change. Like, are we just losing a little bit of heat of the ice, or is the ice gaining a little bit of heat that would cause melting? Well, now we're getting down to the error of the instruments. And this might be something that Matt or Hassan might have said, that we can measure the wind speed, say, to 5%, which is great. But when you're right around the hinge point, 5% might be the difference between melting and nothing. So that's where it gets really difficult.
So every year,
And by the way,
go ahead.
and I can go on,
Oh, yeah?
but I
No,
won't.
please.
No. I don't think you have enough film.
Right.
But there's a lot of issues kind of like this.
Well, what I was going to say is that then every year, it seems, and correct me if I'm wrong, a lot of people come down to the valleys to do research with the LTER and to kind of maintain these met stations and things. And I wonder if you, and you spoke also about, before we started filming, about how wonderful experience it is to be on a glacier. Can you speak to why it's important for people? You've got these automatic met stations, and they could be sending data, automatically, and people wouldn't have to spend the money and the trouble to come down here. What is it that's beneficial about people actually being in the valleys, and what kinds of things are important about that?
Well, for us, there's kind of two ways to look at it. One is just the maintenance of the instruments. Because, for example, measuring the sunlight with a sensor that's like this. Well, if a windstorm comes along and it bends the sensor, we wouldn't necessarily know that. We would just say, oh, it's getting a lot cloudier or something, So just the basic visits to the stations really help. But also, just because you have the data doesn't mean you understand the system. It's important to come down and view the landscape, and in our case, view the glaciers and seeing how the glaciers are reacting to these changing environments. And that kind of feeds into our understanding and kind of non-quantitative